So we go on to talk about interarrival time distribution as we still consider Poisson processes. Of course, we've come across interarrival time in every video we've been. This is the third video on Poisson processes, and we've talked about interarrival time everywhere. And here we're focusing on the distribution of interarrival time. So this lesson provides a comprehensive and systematic explanation of inter-arrival time distributions, including theory, intuition, worked examples, and simulations. So we talk about the definition of inter-arrival time. Suppose events occur at times T1, T2, T3. The inter-arrival times are defined as X1, which is T1, X2, that's T2 minus T1, X3 is T3 minus T2. In general, Xn is Tn minus Tn minus 1. So interarrival time represents the waiting time between consecutive events. So the applications of we can find applications of interarrival times in many fields like queuing systems. We're going to talk about queue theory as we move on in this playlist talking about stochastic processes. So we have queuing systems for customers arriving. Then we have telecommunications for packet arrivals. We have reliability engineering, that's time between failures. And we have finance, time between trades, like that. And then we have some key assumptions here. In classical models, interarrival times are independent and they are identically distributed, IID. So this simplifies modeling and leads to tractable results. So let's talk about exponential distribution, which interarrival time tends to follow. The most important interarrival time distribution is the exponential distribution. So, and the probability density function, PDF, is f of x equals lambda e raised by minus lambda x. And x is greater than or equal to 0, where lambda is greater than 0 is the rate parameter. So that's the rate parameter. That's the arrival rate that we've been considering all along. So you see, the number of people arriving follow Poisson distribution, whereas the inter-arrival time follows exponential distribution. Yeah, we talk about mean and variance, right? So for an exponential distribution, the expected value of x is 1 over lambda, and the variance of x is 1 over lambda squared. So the interpretation is that large lambda leads to short waiting times, and small lambda leads to long waiting times. So, and we have a memoryless property, which is the whole idea of Markov, right? So the exponential distribution satisfies that probability of x being greater than s plus t, given that x is greater than s, is simply equals probability that x is greater than t. And this means the future waiting time does not depend on how long has already passed, you know. So, and then we have the connection of that to Poisson process. So if events follow a Poisson process with rate lambda, then number of events in time t is Poisson distributed. And then we have inter-arrival times to be exponentially distributed. So this is the fundamental result in stochastic processes. So we see that inter-arrival time now has a connection with Poisson process. So we have this now. Given that lambda is 2, that's arrivals per minute, or whatever time step you want to use. So find probability that x is greater than 1. So for x to be greater than 1, we follow so we have probability x greater than x to be e raised per minus lambda x, right? So we have e raised per minus lambda x. So probability that x is greater than 1 then is equal to e raised per minus 2 times 1. That's e raised per minus 2, which is approximately 0.1353, like that. Now, still talking about the memoryless property now, probability that x is greater than 3, given that x is greater than 2, we using memoryless property. Probability that x is greater than 3, given that x is greater than 2, is simply probability that x is greater than 1. And that is simply e raised per minus 2. This shows that past waiting time does not affect future probability, right? So in that case, we can simulate this whole thing. Lambda is 2, blah, blah. And then get, so we get we get our plot exponential inter-arrival times, which is given here. And then we have sample mean and theoretical mean, roughly the same thing, like that. Okay. So how do we simulate a Poisson process? We can simulate arrival times by summing inter-arrival times. So Tn, we already know that xi is equal to t. Okay, like, yeah. we don't summing it at Rabat times Tn is equal to summation from I equals 1 to n of xi. So lambda is 2, time is 0, and you now do that for every time step. So for all the interarrival times now, you have all of this now, you know. So T1, T2, all the way down to the last, like that. So we can then talk about other interarrival distributions. Okay, did I even run this? Yeah. So this gives us interarrival times. So, and that's 1 over lambda, exponential of 1 over lambda. So that gives us all these values. So when we get to Q theory, there'll be more clarity on some of these concepts. So other interarrival distributions that we can have. Not all systems follow exponential distribution. Examples, we have deterministic systems where x is equal to c. So there's a constant value there. Then it can also be uniform where x is uniformly distributed over AB. Then you have gamma distribution where some of exponential variables x is a gamma follows gamma distribution with parameters k and lambda. And we can also have Weibull distribution, which is used in reliability modeling, as you're going to see later, I believe. Then when exponential models fail, when do exponential models fail? The exponential model may fail when events are not independent. So if events depend on themselves, the exponential model can fail. Then systems have memory. So if there's a need for memory, then this exponential system fails. Human behavior introduces bursts and systems follow schedules. So imagine example 3, where you have this, that lambda is 0.5 and you need probability that x is less than or equal to 3. So probability x is less than or equal to x is 1 minus e raised per minus lambda x. So that means probability x is less than or equal to 3 is 1 minus e raised per minus 0.5 times 3, right? So that's 1 minus e raised per minus 1.5, which is 0.7769, like that. So we can also simulate that here. So lambda is 0.5, and we are checking this over x is 0 times 0.5, 0 to 5, right? So CDF is 1 minus exponent of minus lambda x. So we get this thing that looks like a saturation curve a bit. So in summary, we have that the PDF for Poisson distribution, which interarrival distributions follow. Is it Poisson or exponential rather? So f of x is lambda e raised per minus lambda x. The mean is 1 over lambda. The variance is 1 over lambda squared. And the survival is probability that x is greater than x. That's e raised per minus lambda x. The cumulative distribution function is 1 minus e raised per minus lambda x. So the key idea here is that exponential interarrival times model completely random event timing. So we have practice problems. So define interarrival time and express xn in terms of tn and tn minus 1. Of course, interarrival time is time between events, like that. So xn will just be tn minus tn minus 1. If event occurs at t1 is 2, t2 is 5, t3 is 9, find the interarrival times. So that means t2 minus t1 will be 5 minus 2, 3. Then t3 minus t2 will be 9 minus 5, which is 4. So explain why interarrival times are often assumed to be independent. Of course, they happen independent of each other. Then you have exponential distribution. Given lambda is 3, write the PDF of the interarrival time. So, of course, that is f of x equals lambda e raised per minus lambda x. So now lambda is 3, so you have 3 e raised per minus 3x. So compute the mean inter-arrival time when lambda is 4. So the mean inter-arrival time is 1 over lambda, that's 1 over 4. That's 0.25. Compute the variance when lambda is 0.5, that's 1 over lambda squared, that's 1 over 0.25, I believe. You know, that's that's 4, I think. Then find P of x greater than 2 when lambda is 1.5. So that would just be e raised per minus 1.5x. Then find P of x less than or equal to 3 when lambda is this. Okay, yeah, this will be so x less than greater than 2 will be e raised per minus lambda x. That's e raised per minus 1.5 times 2, that's e raised per minus 3. We have all those here already. So if it's greater than, you have you go straight. If it's greater than, you have e raised per minus lambda x. If it is less than, you have 1 minus. We saw that also in another example. So in that case, you have if it's less than, you have 1 minus something something. So you want to try all of this out. So greater than x now. So you have e raised power minus 1.5 times. So that's e raised power minus 3. Then less than, so you have 1 minus e raised power minus lambda. That's 1 minus e raised power 3 times 0.8. That's 1 minus e raised power minus 2.4. Then you have memoryless property. So you want to try your hands on all of these things and see how well you get the gist. Let me know how helpful all of this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I thank you very much for that. If you haven't subscribed, question, what are you waiting for? Go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. Try your hands on the practice problems. Here you have questions 1 to 10, questions 1 to 10 right here. Then 11 to 20, like that. So try your hands and be sure you get the gist properly. Let me know what your answers are, if possible, in the comment section, either on Facebook or on YouTube. Yeah, so you can become a member of the channel by clicking on join. That gives you special privileges like getting to see some videos first or getting to see some videos exclusively. All right. Ultimately, don't forget to comment, like, share so that more people can have access to the great content I have here. Till I come your way again, keep doing maths right. Bye.